Hi everyone, welcome to GemChem. Now today's video is on synthesis of pyrrole, and in this particular video we are going to deal with Knorr synthesis. Now already 3 videos are uploaded in channel. You can watch it on heterocyclic chemistry. I will give you the link in the description box as well as the I button present about this video. And if you are new to GemChem, do not forget to subscribe the channel and hit the bell icon for regular updates. Now let us start. So first, in Knorr synthesis we are going to deal with alpha aminoketone and beta ketoester, from which we are going to obtain our pyrrole ring. So in this case, how retrosynthetic pathway is followed? If you consider this one, the breaking of the bond takes place like this. This one gets broke and this one also. Finally, what we get is this components. If we want to show the charge distribution, certainly for Knorr synthesis, we are going to consider this carbon to have a negative charge and the corresponding adjacent carbon as the positive charge. And one which is present here is considered as positively charged carbon. Similarly, another complementary synthesis of Knorr synthesis is there, which is Hans synthesis. In that case, we are going to see that instead of this carbon being negative, this will be positive and this will become negative. So what are the starting materials? So you can see here, this is beta keto ester and this is your alpha amino ketone, which will be our starting material. So when we try to see the mechanism of this particular reaction, we can consider this as, suppose we have these groups and here it is R1, here it is R2. We add to it alpha amino ketone, here we have NH2 and here we are going to have R4 group and R3. So first ketone and amine will react and it is going to form a bond like this. Rest part remains as it is. This will be R3, this will be R4. This will be your R1 and here we are going to have R2. Now this will undergo equilibrium to form another type of species where double bond will come here. Hydrogen will be lost from your C. This will be R3. Here we have R4. This hydrogen which is lost here will become your NH. This one will remain as R2 and this one will be R1. Here a double bond will also be formed because their ketone reacted with amino. So here a double bond formation has occurred. Now the hydrogen which was present here traveled here and this opened up. As a result, hydrogen came in this side. Next we are going to see that here the lone pair which is present will undergo reaction. So this will come up here, this will be donated this side and this will open up. Finally, what we get is this structure. N, double bond, here we have OH, R3, here we have R4 and in this side we have R1, here R2. What will happen is that from here OH minus will go away and from this side hydrogen will get out. As a result, after removing a water molecule, we are going to get this structure. Here we have R3. Here we have R2, this is bond, here we have R1, there will be a double bond with nitrogen and here we are going to have R4. Finally, there will be shift of proton to form our final product, that is pyrrole ring N. Here we have H and here we have R4, R3, R2 and R1, and this part will have a double bond and this part will have a double bond. So this is the general mechanism for Knorr synthesis, but here certain things are to be kept in mind. That is, one thing, alpha aminocarbonyl compounds are generally very reactive. They tend to dimerize with each other and thus we generally prepare them in the form of salts so that they do not undergo self-condensation. In Knorr synthesis, we need a very good methylidine group. The methylidine group which we require should be highly activated. So in that case, when we are considering the methylidine group, that is one which is this portion, yellow portion, it is attached with R2. So that group may be replaced by any kind of aryl or RCO group to get it activated. Similarly, in this case R3, if we take any kind of alkyl group, the result will be very poor. And if R1 is taken as hydrogen, then also the result becomes little bit poor. So we need a ketone part in the double bond O rather than a aldehyde part. So first let us see one of the compound synthesis. So if you consider this one, in this case you can see here that NH is present and here we have a methyl group. How to synthesize that? We are taking a alpha ketoamine, and in this case we are taking beta ketoester. Now we add to it aqueous KOH at room temperature followed by acidification. We are going to get the structure like this. If you see here, CO2Me has already been converted to CO2H. Now in the next step, decarboxylation will occur and this one will convert into CO2H. As a result, we are going to further add more amount of aqueous KOH to continue the reaction. So once we add aqueous KOH and continue the reaction for 1 day and followed by acidification, we are going to get that this CO2H has been removed and this CO2ET has been converted into CO2H. Further on heating, this will undergo decarboxylation and we are going to get our desired product. So, since we have considered a factor to avoid self-condensation, here we have taken a formation of in situ alpha ketoamine so that they do not form any kind of dimer product. The starting material here taken is a salt. In the next case, we are going to see that this alpha aminoketone is being prepared in different form. It is formed in situ so that it reacts with the second component easily. In this case, reagent is used zinc acetic acid or sodium diethionate, which helps to reduce the oxamino group to amino group while leaving ester groups untouched. So let us see how this occurs. Our target molecule of pyrrole is this one. So if we first take this part only this part. So we have CO2ET followed by a carbon CH2, C double bond O, and this is our methyl group. We will provide it with NaNO2 so that this part becomes, this methylidine part converts into double bond NOH. Once this has converted into NOH, another molecule of this one is being taken. On adding zinc acetic acid is going to convert the NOH group into NH2 group. So same thing has occurred, NH2. Next we are going to add water to it. Once we add water to it, it will fuse together. So this part will react. As you can see here, NH bond will be formed between the two chains and further reaction will result in loss of more amount of atoms. So in this case, what we see is water molecule is being lost. In the next step also we are going to see that there will be loss of different parts. Now what will happen? Here we have a lone pair. These lone pairs will be given up here. This double bond will come up and react with the ketone and the double bond oxygen will open up. Once this occurs, our next intermediate will be this part. In this case also there will be loss of a proton as well as a loss of hydrogen. So here we have a hydrogen. This hydrogen will be lost and this will open up. Similarly, here we have hydrogen will be lost and this will be opening up. Finally, the product obtained is this one. glance we can consider that why we should take a beta ketoester. Why not we take only a ketone? But this is impractical. Why this is impractical? First condition is that there is a possibility of formation of two different pyrrole derivatives using an unsymmetrical ketone, first case. And second case also, the methylene group of the ketone will be inactivated, it will not be so reactive. As a result, self condensation can easily take place. These two conditions prevent the usage of only ketone. Try to obtain the starting material for these compounds which I am providing you. CO2 ET, this one, another one will be your N, you have CO2 ET, here you have CO2 ET and C5H11. So the question will be, find the starting material for these two products, and this one will be the checkpoint for this video. So hope this was helpful. Thank you for watching. Do not forget to like, share, subscribe and comment.